This is CPE 233, lecture 22. I'm going to go review experiment 8, a couple more details there. Additionally, we're going to talk about some standard computer architecture issues and then work through an example. So the experiment 8, we had to multiplex the displays, and so what we're going to do, what that means is, by the way the displays are wired, which is arbitrary on that board, you can only put one of the same number on those 4 displays at the same time. Now, the way we make it look like a normal display is we turn one digit on at a time, but we do it fast enough to look like there's multiple digits on, which takes advantage of the human visual system, retinal persistence or persistence of vision. So there are a couple issues that arise if you don't do it right, like ghosting and flickering, but it's very straightforward. This is the algorithm to accomplish that display multiplexing and do it right. So before I do anything, I want to turn off the anodes. Then I put new segment data there. Then I put the anodes back on. Then I wait. So this is essentially one column for the 10s and one column for the 1s. As you can see, they're very similar, and you can take advantage of that when you're writing the code. You need to keep track of a count in experiment 8. The easiest way to do it is keep track of the count in decimal, which takes a little bit extra code, but it's still less code than converting a binary to decimal each time you need to display a number. The best way to do this is keep 2 different counts and 2 different registers and makes your code very simple. This experiment uses a lookup table, which is a super efficient way to we'll say access data. The data you're accessing in the experiment is the 7-segment data, which is going to be based on the BCD count, which is a 4-bit count. Super fast way to do it, very similar to arrays in a programming language. You need essentially an index, so you need what we're going to index into the lookup table just same way you index into an array. It's actually kind of the same object, but that's another story. It's relatively simple to do. It's really tricky the first time you do it, but don't let that scare you off. Looks like we've seen that one. So, computer architecture. So, there's a couple different words you got to take away from this class, different terminology, and one of them is like a high-level design of computer architecture. So, generally speaking, there's 2 different versions out there. There's a von Neumann architecture and a Harvard architecture. Now, if you tell someone you took an architecture class, chances are they're going to ask you a question like this. And even if it's strict memory, you got to memorize this and take it away from the class. It will come up again. Now, the difference between these is, in a von Neumann architecture, there's only one memory shared by both data and program. In a Harvard architecture, there's 2 memories, one for data and one for a program. Now, these are the differences. The idea of von Neumann was, and Harvard, whatever, and those, I think it was in the 1940s, Harvard and Princeton had a computer design contest, and this is the designs they come up with, and it stuck ever since. So this is also sometimes known as the Princeton architecture. Now the technical definition is a little bit, I think it's a little bit slightly different, but this is good enough for us. Harvard has 2 separate memories. Von Neumann, 1 memory for both data and program. The other notion that we deal with often is the notion of RISC versus CISC. So obviously RISC-V is a RISC processor, but we haven't really talked about what that is. RISC stands for Reduced Instruction Set Architecture, and it's very misleading. There's also CISC architectures out there, complex instruction set architecture. So the issue here, a couple issues here, is reduced instruction set is a misnomer because it has nothing to do with the number of instructions. It has to do with the complexity of the instructions. So if I have a RISC architecture and add 1,000 more instructions to it, and they're simple instructions, it's still going to be a RISC architecture. It has nothing to do with the number of instructions in the instruction set. Generally speaking, RISC has simple instructions that execute fast, and so you'll need more of them to get your program done compared to a CISC architecture. CISC architecture is going to have less instructions, maybe, not necessarily, but those instructions are going to be more complex. So you're going to be able to write your program using less instructions. But since those instructions are more complex, it's going to take longer for them to run. And those are the trade-offs. So generally speaking, by definition, this is what a RISC is, and a CISC is essentially the opposite. RISC, simple instructions that typically operate in the same number of clock cycles, and we saw this in the RISC-V Otter, where all of our instructions executed in 2 clock cycles except the load type instructions. Generally speaking, RISC architectures have a large register file for data. CISC architectures generally don't. They rely on swapping data back and forth from memory, which is certainly a way to do it. Saves registers, but it has its own issues. Typically, since the instructions in a RISC architecture are more simple, RISC architectures generally can take a faster clock speed. So like I said, CISC is pretty much the opposite of all this stuff. This is important. This is another thing. I don't know. You got to take it away from this class because once again, someone's going to ask you that. So these are kind of what I generally remember. But the idea here is what's better, RISC or CISC? Well, if one of these was better than the other, then the less better one would go away. So this is an ongoing long-term argument here. We have both RISC and CISC architectures, which pretty much declares that there's not any 100% case where one's always better than the other one. If you're designing a custom architecture to solve your custom problem, you may want to choose one or the other one, but that's up to you, the designer. Certainly when you pick up a new computer, typically you look at see what type of architecture it has, and it generally states it even in the high-level documentation. So data path, these are things you should know, but I technically always forget them. And data path and central processing unit. So my claim is that I understand how the RISC-V works. I understand the architecture and what it does, but the notion of data path and CPU are definitions I can't remember, and I swear they're not really solid definitions. I think when you read it in different places, the data path or the central processing unit are essentially different subsets of the same architecture, and I can't remember what they are. We often, we talk about CPU quite a bit, central processing unit. Oftentimes in a modern computer, there's not a central processing unit. There's multiple processing units. Central processing units is a kind of a dated term. Back when hardware was so expensive, you had one piece of hardware that did all the data crunching. Okay, well, that's generally not the case anymore. CPU, data path, you often hear that in context of truly just the path of data, but it actually has a different definition when you use it in the context of a computer architecture. So I won't test on these because I can't remember them. I will test on your just ability to know the RISC-V architecture in general. But you should generally know these terms and kind of be able to toss those words out there in an interview or a party or whatever you do. So this is an example problem, and it's actually done in another video. I've left it in here simply because the solution is here and it's not in the other video. So here is a viable solution. But what I wanted to do is go on to this next problem here, and essentially this is a problem that calculates the parity of a value in X10, and that parity is returned in X10. So it's a subroutine where you send it a value in X10, you change that value, and you send just the parity back. So 1 indicates odd parity, and then 0 indicates even parity. So I'm not going to do these, but I have they're done in the book, and I have some standard solutions here. So I thought we would look at this real fast, and it's a working solution. Essentially, this solution, what it does is, it says, well, registers are 32 bits. I'm going to look at each bit individually. So necessarily there's a loop in here that is executed 31 times. 32 times actually. Okay, so, and it's essentially just counting the ones in this. So what I want to do is just count the number of instructions in that are executed when I call this subroutine. So this is going to be 2 and 2, 1, 2, 3, 4, 4 times, and there's let's see, 4 instructions. There's 2 clock cycles each. It does this 32 times, and this loop here plus 1 to for the. I guess I should look at the problem first. So this ain't 4. It's actually 6. 1, 2, 3, 4, 5, 6. Each of them are 2 clock cycles each. I have to do this 32 times, which is once for each bit. This 1 here is the BEQ at the bottom. So this is going to be 2, 2, 2, and 2. So it looks like all the 2's are going to be, let's see, 10 plus 12 times 32 plus 1. 380. Total instructions 384 plus 10 equals 394 instructions. Okay, so that's fine. But let's explore another way to do this. And what the problem is we're going to use a lookup table. Okay, so what the lookup table is going to do, what the approach is, I'm only going to look at 4 bits at a time, and I'm going to use that as access into the lookup table to find how many bits are set. So here's my lookup table, and this is the way it works. This is 0, 1, 2, 3, 4, 5, 6, 7. And so this represents a 0, 1, 1, 1, right? And in here, there's 3 bits set. That's where this 3 comes from. 6 is 0, 1, 1, 0. There are 2 bits set. That's these 2 bits. 5 is 0, 1, 0, 1. 2 bits set. That's where this comes from. So this is a table indicating how many bits are set in a given 4-bit chunk. So that's our lookup table. And so the code, and I'm going to toss this in my code here in the data segment. What I need to do in this code is consider 8 4-bit chunks, and those 4-bit chunks are going to be, I'm going to use the lookup table to see how many bits are set in those 4-bit chunks. So obviously I'm iterating 8 times instead of 32 times, so there's going to be a direct savings here. Now each time through, what I'm going to do is access the lookup table. So here is the access to the lookup table. I'm declaring everything but the bottom bit. I'm adding that bottom bit to X30, which is the address of my lookup table. So X30 plus the value in that bottom nibble, that bottom 4 bits, is going to be my offset into the lookup table. And what I'm going to do here is I'm going to load that value. I'm going to go get that value, and then I'm going to add it to my running total. And that's the way I'm going to do this problem. So let's look at this. This is going to be, roughly speaking, 2 plus 2 plus 2. This isn't actually 2. This is actually a load address. It's going to be 2 instructions, but we're going to pretend like it's only 2 clock cycles. And this is 1, 2, 3, 4, 5, 6, 7, 8. 8 instructions. There are 2 cycles each, and I'm going to do it 32 times. Not going to do it 32 times. I'm going to do it 8 times, and then I'm going to check this one more time. So it's 8 times 8 is 64, plus 2 times 2 is 128, plus 1 is 129. So this is all 129. And so this is going to be 2 plus 2, 129 plus these outside values, which is 10. So total, this is going to execute in, this is actually 2, not, it's 130 plus 10. So this is 140. How's that? Okay. 140 instructions, okay, and great. The idea here is the previous slide, a previous version, it took us 394 instructions. So by using a lookup table, this thing runs in just about 1/3 of the time. So this is something advertising how the lookup table works. Keep in mind, I would be more familiar with this code. What it's going to do is take that value in X10 and continually, it's shifted right by 4 bits, and you can see that shift right here, 4 times each to look at the nibbles individually. So this will look good. This lookup table is based on nibbles. If I based it on bytes, the table would be 256 values in it, but that would change this to a 4, and it would run much quicker, but at the expense of having a bigger lookup table. There's always going to be a trade-off with lookup tables, but they're, generally speaking, if you know what you're doing, you can make them work quite well.